Let me just make a couple of comments around this. I'm really excited about this work of using deep learning to integrate production history. And I think what Honggeun has done here is quite revolutionary. It's going to change the way we do production history matching. Honggeun, go ahead, take it away.
Hello everyone again, and this time I will be talking about the machine learning assist the history matching for deepwater lobe system. And in this project, Santos, Javier, Wen, and Dr. Birch have been participating. Here are the executive summary. Rule-based modeling method enable direct integration of the geological concept, which is really good. However, there has some limitation of the data conditioning. That's how we propose a machine learning assist the history matching workflow for rule-based modeling method by combining the GAN, Generative Adversarial Network, and the Ensemble Kalman filter, EnKF. And GAN enables the represented high-dimensional reservoir model with a few numeric value that successfully find the ensemble that optimize reservoir model that honor the realistic geological heterogeneity and production history. We can expand the GAN assist with the Ensemble Kalman filter to various history matching problems, including the geothermal or development of the CO2 storage. Here's the agenda. In the introduction, we will review what are the rule-based model and their remaining challenges for the data conditioning. In the methodology, we will review the GAN and the Ensemble Kalman filter, and in the end, we will explain what are our suggested methods. In the result part, we will see one demonstration for the 3D rule-based model for deepwater lobe system, and in the end, we will summarize it again. So, unlike the conventional geostatistical methods, such as the barogram-based or multi-point statistics, rule-based models simulate the sediment dynamics to generate the reservoir architecture. As a result, it can capture more realistic geological structure and heterogeneity in their subsurface models. Moreover, rule-based model enabled integrating the associated geological concepts, such as the geometry of the depositional element, or stacking pattern, heterogeneity, or hierarchical trend, into the reservoir model directly. Here are two examples of the rule-based model. On the left-hand side, it's from Birch and Deutsch in 2005. It's a cross-sectional view of the submarine fan. And on the right side, it's a 3D view of the thickness model, which is also for the deepwater system. In more recent work, the rule-based model has been referenced by a variety of different names, such as event-based, hybrid, surface-based, but they are using the same concept in making the reservoir models. And Birch compared the rule-based model with the conventional geostatistical methods, such as the barogram-based or multi-point statistics and object-based method. So in this chart, each black dot indicates the individual reservoir modeling method, and the x-axis indicates the different ability. So if it's to the left, it has more ability to condition them to any given data, and then as it goes to the right, it has more ability to replicate the realistic geological features. So this is kind of the trade-off for now, but there's no such solution which are realistic enough and at the same time perfectly conditioned to the reservoir models. So from the conventional geostatistical method, by integrating the stacking patterns or forward model for sediment or topographic update, flow vessel of the sediment, we can integrate more and more geological concepts. That's how it becomes a rule-based modeling method. So as we go to the right side, it has not many ability to condition to the given data, and production history is one of the remaining challenges for expanding the application of the rule-based model. Here are a brief workflow of the rule-based models. On the left-hand side, we are looking at the flow chart, and here we need to start from defining the initial bathymetry, reservoir extent, and lobe element geometry. In this demonstration, we are going to use the isotropic lobe, which can be defined by their radius and the maximum thickness, as you can see in the right-hand side. And from there, from the first topography of the bathymetry, we compute the probability map of the center of the next lobe. And with the probability map, we apply the Monte Carlo sampling to assign the next well location. And depending on their location, we update the topography. And this is iterative process. We do this until we fill out our reservoir extent with a depositional element. And on the right-hand side, it has one example of 3D view of compositional surfaces, which are made from the multiple lobes. And then bottom figure shows their cross-sectional view. And in the end, after we defined the compositional surface, we assigned the petrophysical properties such as the procedural permeability using the hierarchical trend model from Hertz in 2004. So this is one example of the permeability model, which are made by the rule-based model. We can observe the two different hierarchical trends. The center of the lobe are having the higher permeability than their boundary, and also the lobes on the bottom have the lower permeability than the upper lobes. That's because it's compaction impact. So objective in this presentation is to develop the machine learning assisted history matching workflow so that we can integrate the production history to get a better reservoir model in the end. And to do so, we are going to explain the GAN and Ensemble Kalman filter in the following slides. Let me get started with the Ensemble Kalman filter. Ensemble Kalman filter is one of the most popular ensemble-based history matching algorithm, and its variation is Ensemble Smoother or ESMDA. So Ensemble Kalman filter, ESMDA, or Ensemble Smoother, they are in the same family. So instead of using one determinate reservoir model, it used multiple realization of the reservoir model, which is called ensemble. And in the Ensemble Kalman filter, we represent each realization with a state vector. And each state vector consists of the static parameters and dynamic data. Static parameters are the porosity or permeability, which doesn't change over the time. And the dynamic data can be a production estimate from the wells or saturation or pressure, which are time dependent. So in this notation, capital Y indicates the state vector matrix, which are the set of the individual state vector, and each state vector indicates individual realization. And if you look into one state vector here, it is simply consists of this static parameter and the dynamic response. And there are two main steps in Ensemble Kalman filter. First, we need to predict. We need to predict from this static parameter to their next time step dynamic response. And then once we get this dynamic response, we need to compare them with our actual observed production history. And we need to update our ensemble using these assimilation steps. In the assimilation, they are using the Kalman gain, which are given as here K, and this Kalman gain are mathematically defined in the following equation. And this is designed to minimize the error covariance among the realization. And here are the schematic diagram. From the initial ensemble, we predict it for the next time step by comparing their estimated result and our actual observation. We assimilate it. And then from the updated model, we predict it one more time. And then we do this iteratively until the end of our production history. And next, in this slide, I would like to explain the Generative Adversarial Network, or GAN. GAN is a framework for training the generative model that was suggested by Goodfellow in 2004. It has two different neural nets. First is the generator, the second is the discriminator. This generator takes the latent random vector and map them to the image space. In our example, this should be 3D subsurface models. And this discriminator takes the image data, which is subsurface model, from either training data set or from the generator, and it can tell whether it's true or not. If it's from the training data set, it's true, otherwise it's fake. So discriminator is trained to tell which one is real and which one is not, and the generator is trained to fool the discriminator. And they are making this competition over the training process, and that's why it's called the adversarial network. And this competition can be explained by this mathematical expression as shown here. And this is internal structure of the GAN, the generator. So it starts from the 100 latent variable, and each latent variable are sampled from the normal Gaussian distribution, which is 0 mean and 1 standard deviation. And we can consider this as a random seed. And from there, we expand our hidden layer or expand our feature map step by step. And in the end, we will get the same dimension as our subsurface model. In this case, 28 by 28 by 20 in width, length, and depth. If it was a standard Ensemble Kalman filter, we will update the ensemble's petrophysical property directly. For example, in this example, we have the permeability, and we have a multiple realization, maybe 100 realizations here. And from there, we run the reservoir simulation to get the next time steps well oil production rate. So WOPR is the well production rate, and we will use this WOPR in doing the history matching. So from there, we will design the state vector, which are a combination of M and D. And by comparing the actual production history, we can update it by using the Kalman gain. And we do this iteratively until the end. And after we finish this history matching process, we predict for the future forecast. One limitation of this method is that, as we've seen in the earlier slide, this rule-based model have bimodal distribution in permeability, because it has sandy rock in the center of the rock and the shaly rock on the boundary. So this is not compatible with the fundamental assumption of the Ensemble Kalman filter. Ensemble Kalman filter is mainly based on the Gaussian assumption. So it automatically assumes that each property are following the Gaussian distribution. So even though it was not Gaussian in the beginning, it will end up with the Gaussian permeability, which will damage all the geological features we had in the beginning. That's how we suggest this GAN Ensemble Kalman filter. So instead of updating the permeability right away, we're actually updating these latent vectors, which are input for the generator. And as I explained earlier, this Z are drawn by this standard normal, standard Gaussian distribution, which is perfectly compatible with the Ensemble Kalman filter's assumption. So in the beginning, we will generate the multiple set of this latent vector. And from there, we use the trained generator to map them to the permeability. And also from there, we can run the simulation. And then we design this state vector. Here, we are not using the M anymore. It's a G, which is latent vector. And we update this Z, not this M. So that's how we updated this ensemble, and we do this iteratively. And after we finish this process, we also need to predict the future production. Here are one demonstration. On the left-hand side, we are looking at the 3D rule-based model, which are the truth model. And then in the bottom, we have their bimodal lobe permeability distribution. And for building this the rule-based model, we assume the 750 radius of and the 4-meter maximum thickness of the lobe element, and its perfect compensation sticking, and the min max of permeability and their standard deviation. And there are some more contours for this reservoir simulation alone. And we have one injector in the center and 4 producers in each corner. So basically, we are gonna use the 500 days WOPR in each 4 producers, and then we updated our ensemble to predict the simulation up to 2,500 days. And here are the results. On the left-hand side, we have the GAN Ensemble Kalman filter. On the right-hand side, the standard Ensemble Kalman filter. As we expected, standard Ensemble Kalman filter end up with this normal distribution, which remove pretty much of all the boundary of the lobe element. So even though we had a lot of the effort for making the really realistic reservoir model, but it ended up with a non-realistic. It become the non-realistic. It become non-realistic reservoir model in the end. However, GAN Ensemble Kalman filter, even after we updated this ensemble, they still preserve all the hierarchical trend and also their low boundary and also their bimodal distribution. And also we look into our well production performance. So on the left-hand side, again, it's GAN Ensemble Kalman filter's result. On the right-hand side, it's standard Ensemble Kalman filter. So the light grays are the initial ensemble, and then the dark blacks are the updated ensemble. So we have a 100 realization. That's why we have 100 lines for each. And these red lines are the reference prediction. And in updating this ensemble, we use this information up to 500, and from the 500 to the 2050, we haven't used that information to update the ensemble. So from the wide range of the uncertainty in the initial ensemble, GAN ensemble Kalman filter successfully reduced their uncertainty, and it also gives us the very accurate result, which covers pretty much of this reference case. However, standard ensemble Kalman filter, they may shrink to too much uncertainty, and their results are inaccurate compared to the reference. We look into the pressure at the well location, and we also observe the similar outcomes here. So again, the GAN ensemble Kalman filter, they successfully reduce the uncertainty and match the reference, but this standard ensemble Kalman filter, they has a huge misfit in the well number 1 and well number 3, especially because we already used the information up to the 500. So at least they are supposed to match the first 500 prediction, but their results are not very good in the end. As a quality assessment, we map high-dimensional rule-based model or the ensemble to the 2D space using the multi-dimensional scaling. So, and by looking at the multi-dimensional scaling plot, we can compare their dissimilarity or similarity. If they are close together, that means their realization are similar to each other. If they are further, they are not. So light gray are the initial ensemble, and the red are the reference model. After we update the GAN ensemble Kalman filter, they successfully move their ensemble near the red point, and also they shrink their uncertainty somehow. But on the right-hand side, standard ensemble Kalman filter, they don't have much significant update in the end, and there's not many points near this reference model. Here are the key points. GAN enables effective dimensional reduction for the high-dimensional reservoir model, and also it can preserve all the geological concepts we had in the beginning. And then the generated input, which is related to random vector, follow the Gaussian standard normal distribution, which are compatible with the fundamental assumption of the ensemble Kalman filter. Therefore, GAN ensemble Kalman filter outperform the ensemble Kalman filter in accuracy of the prediction, and also GAN ensemble Kalman filter ensure the geological consistency with the initial ensemble or training data. GAN ensemble Kalman filter is readily available for different types of reservoir, because GAN and ensemble Kalman filter doesn't have any constraint itself, so we can apply this scheme to any type of the reservoir model, such as the fluvial channel or the deltaic reservoir. Thank you for listening. This is what I prepared today. And if you have any questions, please let us know. Thank you.
Honggeun, thank you very much for an excellent second presentation. Appreciate that. Now I can see the chat window is lighting up. A lot of good questions. Tomo, you just asked the question. Do you want to go ahead and just ask it?
Yes. Yeah, thank you for great presentation. It's very interesting and excited new technology, I think. So, how do you make conditional realization by GAN? Can you make it just so latent? Can you make the just initial input of the latent random number only with such a latent number? Can you make the conditional realization, or just that is my question. Yes.
So condition to the history.
Conditional realization means well log. Yeah.
So I haven't covered in this presentation, but the last year we had this semantic imaging painting scheme. So which is basically after, because the only misfit part is that we have one certain well trajectory information, and we don't know, and then that should be preserved over the ensemble. So what we applied here is the semantic imaging in painting. Basically, after we generated this model, we made this void. So we removed all the values near the well boundary. So we removed all the property near the wells, and then in the center of the area we put our well information, and we fill the rest of the missed part by using the semantic imaging painting. The semantic imaging painting makes the rest of the reservoir that are compatible with both well data and the rest of the reservoir. So that's one scheme that we applied last time. And then when also have been working on this project, and he been using the pix to resolve this data conditioning problem in the rule-based model.
Mm-hmm. Okay, interesting. Thanks.
We're happy to ensure that you have access to and can see that work from last year. And of course, we welcome the opportunity to bring Honggeun Joe in and do like a deeper dive and a review of the whole workflow.
Okay, thanks.
No, thank you. Any other questions, comments about this work? Oh, we have a question from Wen Pan, the previous speaker. Wen, do you want to go ahead and just ask it? Do you want to unmute and jump in?
Sure. Yeah, but just a quick question. So I think it might be interesting to like make our model more kind of can generate more comprehensive models to capture more like uncertainties associated with our barograms and trends. I was wondering like maybe our future work can be like use a conditional GAN to like condition our models to different parameters, like in the varograms and trends, for example. We can use like different nuggets, different as our input to like force our models to reproduce those kind of patterns.
Yeah, I think that's going to be our next work for sure.
Yeah.
And what we found is that in the training, again, the more consistency we have over the training data, the easier it trains. So which means if we are importing more diverse input for the ensemble or training data, that it become more and more challenging. And for now, for this one, this is unconditional GAN. For sure, maybe we need to use more advanced GAN technique like the pix-to-pix or conditional GAN, and to tackle that problem for sure. Thank you for your comment.
That's a really good comment. Oh, I see Sarita. I see a comment from you. You're welcome to jump in on mute if you like.
Yeah, I just wanted to say that the morning session. Hi everyone. So the morning session has been really very informative, and especially the GAN stuff. We definitely are much privileged to have access to the resources on GitHub, and what we can do is I can reach out to folks interested in BP to see if they are able to access all these resources. So thanks a lot. And we'll catch up again after lunch. Maybe I'll join a little bit later, but we'll definitely try to join around 2:30-ish.
Sarita, thank you so much. And we appreciate all of your collaboration with Direct and all of your effort with the students. Honggeun Joe has just pulled up his repository on GitHub. And so what you'll see is that there are well-documented workflows. There are all the codes. You can do exactly what Honggeun has done and for all of our students' work. So I think that's essential. I know that often in the browser, GitHub has an issue rendering the workflows. Okay, there it goes.
Mm-hmm.
So this is, I think this is provided to the member of the consortium. And
Yes.
This is one of our demonstration. And here, because it's a distributed notebook, we cannot load a very large data. We just demonstrate the 3D basis model. And then here, it has from A to Z. So it has the workflow to generate the multiple realizations. And from there, how we can parameterize it by using GAN. So I think you can refer to this information, this workflow to demonstrate your to mimic this workflow on your computer for sure.
Thank you, Honggeun. Yeah, so in case I have any questions, maybe I'll reach out to you later, if that is okay.
Okay, for sure. Yeah, anytime. And this is one quick result. So this is from the scan, which is still kept the bimodal phases. And also the PCA and DCT are the conventional dimensionality reduction algorithm. So we compare this scan result with a DCA and DCT. Well, basically, the PCA, they don't capture this discretized value error. I mean, of course, we can threshold it, but even though after we threshold it, we are going to lose a lot of information for sure. And this is from the DCT. So I think the autoencoder or GAN, they are two advancing dimensionality reduction based on the neural net workflow. So
Honggeun, thank you very much for showing that.